So the PELS San Francisco Bay Area chapter was the recipient of the 2022 Santa Clara Valley Outstanding Chapter Award, along with the 2017 Chapter Award, and we were also recently the recipients of the 2022 Region 6 Outstanding Chapter Award, and we were the 2017 PELS Best Chapter Award recipients as well. So today's talk is by Dr. Raghav Khanna here. It's on wide bandgap semiconductor opportunities and challenges for improved modeling and characterization methods in power electronic applications. I'll give an introduction to Dr. Raghav Khanna in a bit. And I'd like to take this opportunity to thank our sponsors. We have TRS Rental Co. here. I'd like to invite them to speak, give a couple of minutes of introduction about their company.
Hello, folks. Both Anne-Marie and myself cover the Bay Area, so it's one of us for wherever you guys are. We are a rental company. It's our primary business. We also obviously do some used sales because we'll have used equipment that we've rented that we sell off. We're known for our 24-hour, 7 days a week, 365-day live person answers the phone. If you need service, you're going to get a real person. There's 8 people in our lab that carry a phone at all times, so you're going to have somebody to take care of that equipment if there's an issue or if you have a question. And we ship same day. We're located at the DFW airport, so we can literally get it onto a plane and on its way to you. And we are giving away some gift cards, so please come and drop a business card. If you didn't bring one, we have some that you can fill out. It's a pleasure to be here.
Thank you. Thank you. And I'd also like to thank our other sponsor, Christine from Johnson Technologies here. And I'd like to invite her to speak.
Hello, everybody. Nice to meet all of you. My name is Christine Dia. I am from Johansson Technology and Johansson Dielectrics. So we are 2 companies. Johansson Dielectrics, we make ceramic capacitors for the power electronics, but we also serve the RF market, which is the Johansson Technology. We are located in a small town in Southern California, Camarillo, about an hour north of Santa Barbara. Today I brought some kits. If you guys ever need, just want to fill your labs with some components, I'm giving this out for free. And if for whatever reason you're not finding what you need here, give me your email. I'll be happy to ship them to you for free as well. So, happy to be here. Thank you.
Thank you. Thank you for this opportunity here. And I'd like to thank our IEEE co-sponsors, the Santa Clara Valley EDS chapter and the Santa Clara Valley CASS chapter. Thank you for your support in getting the word out about these events, and then bringing this talk to your membership as well. And I would like to take this opportunity to also thank Santa Clara University, especially Dr. Shobha Krishnan. As you all know, we had this talk scheduled at the Google campus originally, but then due to some unforeseen circumstances, we had to move the location to this Santa Clara University. So thank you for them for accommodating us on short notice. And this is a list of all folks who made it happen, who helped to make it happen. This is our list of officers and volunteers. I just noticed I need to update it to 2023, so sorry for that. Thanks to the whole team of San Francisco Bay Area chapter PELS here. None of these events would be possible without their support. One thing I would like to bring to your notice is the senior membership of IEEE. If you're not a senior member of IEEE yet, we can help you fix that. Senior membership has a lot of benefits. You get the recognition, you get a senior membership plaque, you get a complimentary society voucher, and multiple other benefits that are listed here. So if you wish to be a senior member and you're not yet, then you can approach us and we'll help you get the recommendation for senior membership grade. So this is 2023 at a glance. This is not the entire list of events, but the list of events for our first half of the year. So we are kicking off 2023 with the talk by Dr. Raghav Khanna here, followed by a talk by Bridge Singh, Kurama Preti, Han Fukle, Keith Kunz, and Stan Helser. So be on the lookout for our emails through e-notice and Eventbrite and multiple other channels that you can be list going forward. And you can also register to be on our email list, and that way we can reach out to you for the events. So you can also check out our new website. We have all the talks listed here. Some of the talks have the PDF slides uploaded, and then we also have the videos that you can watch on YouTube. And you can also follow us on sfbc at _pels on Twitter. And one other means to get to know all the events that are happening in the Santa Clara Valley is through the EGrid. So the link is listed over here. If you go to this, then you'll have an opportunity to register for the newsletter, and you can get all the events, the list of events delivered to your email twice a month. Thanks for again coming over here, and please, I would request all of you to please put your phones to silent mode so that the speaker is not disturbed. And so now let me go over a brief introduction of our speaker today. Dr. Raghav Khanna received the BS degree, MS degree, and PhD degree in electrical engineering from the University of Pittsburgh in 2007, 2010, and 2014 respectively. Raghav has worked for several industries, including Lockheed Martin, PPG Industries, and HRL Laboratories. At HRL, he was directly involved with the development of GaN-based battery chargers for electrical vehicles. In 2015, he joined the Electrical Engineering and Computer Science Department at the University of Toledo. He is currently an associate professor and holds the position of Leidig Family Endowed Professor in Power and Energy Systems. His research interests are in characterization and modeling of wide bandgap semiconductors for applications in next generation power electronics, including renewable energy, electrical vehicles, aerospace and maritime systems, and in low power consumer electronics. He is also conducting extensive research on control strategies for integration of distributed energy resources. He recently received grants from the US Department of Defense, US Department of Energy, NASA, and the JPL to further develop his research activities. So without further ado, I'd like to call upon Dr. Raghav Khanna here. Thank you, Raghav, for coming in here. Let me switch over the presentation.
Sure. Okay, good evening, everybody. Thank you all for being here today. I know that there was some difficulties with the venue change, so I appreciate you rearranging your schedule to have me here today. I want to thank Kishan and the Bay Area Pels chapter for hosting this. Our sponsors in the back, really appreciate that. If there's anybody here from Santa Clara University who's helping with the accommodations, I appreciate that.
She'll be back later.
My good friend and colleague Brian Sainstecker, I really appreciate all he did to arrange this. So I want to just get you to know me a little bit, just so you know who's talking. I got my PhD from the University of Pittsburgh in 2014. My work was in wide bandgap semiconductor device modeling and characterization. During the time I was graduating, I was doing a fellowship not too far from here down in Malibu at HRL Labs. Worked a lot in wide bandgap semiconductors there, as Kishan said. We were directly involved with the development of GaN-based electric vehicle battery chargers. I left the beach. I went back to academia. I spent a year at Bucknell University in the middle of nowhere, Pennsylvania. It's a premium undergraduate teaching school. I was a visiting assistant professor there. After a year there, I took a job at the University of Toledo in Ohio. Also almost heaven. I've been there for about 7 years, and just 2 weeks ago, I became an endowed professor. So I'm really glad to be here. So that's a picture of my dean, and then the gentleman who made the endowment and his wife. So it's the Leidig family endowed professorship. So he was the former vice president of First Energy. So really honored to have that position. I'm here to talk about wide bandgap semiconductors. I hear that's a very interesting topic here. So what we're going to talk about is a need for wide bandgap semiconductors and models. I suspect you all know a lot about this, but I'll just briefly gloss over that. I'll talk a little about the difference between physics and behavioral modeling. There's a lot of tension there. If you go to APEC, you have the folks who like physics, you have the folks who like behavioral modeling, they sometimes clash. I am on both sides, so I'm not here to get into any arguments with either. We'll talk about physics-based models here. Simple edge termination design for vertical GaN diodes using finite element modeling. Hybrid edge termination design for vertical GaN diodes. Again, this is going to be finite element physics-based modeling. We'll do a little bit of behavioral modeling with silicon carbide MOSFETs. You can do physics modeling with silicon carbide. You can do behavior modeling with GaN. These are just two random projects that I picked that I thought I would, or three random projects that I picked that I would talk about. Some applications of wide bandgap semiconductors in space. It's just going to be brief there, and then I'll conclude with some future work. So the hierarchical infrastructure, I think you all know this, it all starts with semiconductors, right? You have semiconductors down here, semiconductors integrated into circuits, circuits into systems. When you talk about simulations of semiconductors often occur at the nanosecond time step. Simulations of circuits often occur at the microsecond time step. Simulations of systems often occur at the millisecond time step. So that's kind of one of the difficulties we have in the modeling and simulation world, where we can have so much fidelity of the model, of the semiconductor device model, but we're not able to import that fidelity at the system model because the system model is only simulating every millisecond, where this guy is simulating every nanosecond. So every time this one takes a data point, it literally skipped 1,000,000, 10 to the 6th points that the semiconductor simulated. So how do you integrate all of this to really show the advantages of wide bandgap semiconductors, gallium nitride, and silicon carbide? That's a challenge we're always dealing with. So try and keep this in the back of your mind as I'm going through this talk here today. I work very closely with the Navy community, also the DOE community, but definitely the Navy. The Navy's talking a lot about power electronic building blocks, a system of systems. You have these DC to DC, they're envisioning an MVDC bus, which is going to have all these DC loads. There's going to be AC loads. So these blocks here, those are DC to DC converters. You need wide bandgap semiconductors. You need power electronics in those power conversions. You have AC to DC here. You have DC to DC, AC to DC, DC to AC. All of those blocks, you need power electronics. So just to give you an understanding of why we need power electronics. Again, I'm sure most of you already know this. What about why do we need wide bandgap semiconductors? We need the higher voltage operating capability. We know that silicon is running out of steam. We need the fast switching capability. The faster you can switch the device, the smaller the footprint can be. The capacitors, the inductors, you can make them smaller with faster switching frequencies, and that's what GaN and silicon carbide and also ultra-wide bandgap materials allow. I keep hitting the wrong button, sorry. High temperature, whether you're out in renewable energy applications, electric vehicle applications, you need that high temperature operating capability. That's where silicon carbide actually has a lot to offer, more than GaN. This is just one of those classic figure merits, specific on resistance on the y-axis, breakdown voltage on the x-axis. The more favorable is down and to the right. So you want a low on resistance, you want a high breakdown voltage. You can see GaN is right here theoretically, silicon carbide behind GaN theoretically. And then the future might be gallium oxide, the future might include diamond, and some other materials as well. But really, a lot of effort being put into GaN and silicon carbide now. In the future, there is some effort being put into diamond as well as gallium oxide, but that's a very, very low technology readiness level. By the way, this is not my plot. This is coming from this reference right here.
Yeah. Is that breakdown voltage per micron or something? Or is it?
No, this is not normalized. The y-axis is normalized. This is specific on resistance. What about applications? Why do we need these devices? Well, those of you who are interested in the EV industry, between 600 and 1200 volts, that's where you see lateral GaN devices, the HEMT devices, the silicon carbide devices, and even some PV inverters as well. But once you start to get up in this above 1 kV, up to tens of kVs, now you're talking about vertical GaN as opposed to lateral GaN. So not lateral GaN HEMT devices, but vertical diodes. Hopefully one day vertical MOSFETs. Obviously we have silicon carbide available in this regime. And then, we want to realize Edison's dream of HVDC distribution. And to get to HVDC distribution, we're going to need these ultra-wide bandgap materials that I was talking about earlier, diamond, gallium oxide, etc. Every material has its own benefit. As I mentioned before, silicon carbide is really great for thermal conductivity, really good for high temperature operation capabilities. GaN's got the higher electron mobility. GaN, theoretically speaking, can go up to 20 kV. Silicon carbide, we think, starts to run out of steam at 15 kV. And then, of course, the ultra-wide bandgap materials go higher than 20 kV, theoretically speaking. That's why we need the research. You can see various different parameters here between the bandgap, the electron mobility, the breakdown electric field, the electric drift saturation, thermal conductivity. What do those affect? They affect things like the switching loss, they affect things like the conduction loss, how efficient the materials are in various applications. So here's where the challenges and the opportunities for modeling are. We want to leverage the high voltage capability of these types of materials. As I mentioned before, silicon carbide we think is running out of steam at about 15 kV. GaN we think can go up to 20 kV if we change to vertical architectures, which we're in the process of doing. As you know, companies like EPC, GaN Systems, they make those lateral GaN HEMTs between 0 and 1 kV. Those are lateral devices. Now the new challenge is to move to vertical architecture so we can start to think about vertical GaN diodes, vertical GaN MOSFETs, etc. There's also the circuit level reliability, realizing application performance entitlement. These devices switch so fast, and that's a great thing. You want them to switch fast. But that fast switching is getting disrupted by the surrounding parasitic inductance. And it's injecting all of this harmonic content, if you will, some frequency content into the system. So you're getting EMI. I think I saw someone's going to talk about EMI soon. You're getting false turn on. You're getting half-bridge shoot through. You're getting overshoot. So it's one of those cases where the device is so good that it's actually not good because the surrounding circuitry cannot handle how fast it's switching. So we've got to get a handle on this realizing application performance entitlement. We're seeing frequency content in power electronics in the near RF spectrum. That's a term that my friend and colleague Dr. Andy Lamont at the University of Alabama likes to say. That there's that chasm that used to exist between the power electronics community and the RF community. It's slowly closing. We're breaching on those frequencies that we've seen in the RF community. So we've got a lot to learn from the RF community. So because of these challenges that we have up here, we need semiconductor device modeling. We need to understand what is the future of these devices, what is the capability of these devices, and how do we start to work around these types of challenges that we have and predict their performance so we can fully leverage their advantages. So this is kind of a simplified list here. It's a lot more complex, a lot more nuanced than this, but I don't want to get into too much technical detail. I've kind of divided my talk today into physics-based models and behavioral models. A physics-based model could be just a bunch of mathematical equations based on first principles. You solve the Poisson's equation to find the voltage drop across the depletion region to write your current voltage characteristics. Or you can use finite element modeling like TCAD. We have a gentleman from Silvaco here, so I know we have a lot of TCAD expertise. You could use behavioral models. Behavioral models based on analytical equations, but with no physical parameter meaning. They're just mathematical curve fit algorithms, but the actual parameters in the equation, they don't have any physical meaning. You could do circuit simulation models. So the general understanding here is that these top ones, number one, they're more accurate, but they're slower. These bottom ones are faster, perhaps less accurate. Another advantage of these top ones is you can correlate observed behavior to real physical parameters, whereas in these bottom ones, you can't really do that. My friends who work in industry and circuit applications tend to like these ones better because they just want to know how the device is going to operate. They don't care what the physics is, they just want to know how it's going to operate. My friends who work in the semiconductor industry who are interested in optimizing device performance, who want to increased breakdown capability. They're more interested in these. I'm interested in both, okay? I'm not here to get into a tug of war with anybody. I've been to conferences where things can get a little funny between the tension between these two types of models, but I'm not here to do that. So let's talk a little bit about about both of these. I'm going to briefly gloss over some of my previous work in this area and then do a deeper dive on these three. So let me say it again. I'm going to briefly talk about some of my work from a very general level in this area and then do a deeper dive on these three so you get a feel for all of them. A couple years ago, we were working with HRL laboratories, and we wanted to write a physics-based model based on analytical equations. So they have this tunnel barrier Schottky diode. It's a vertical gallium nitride diode. We published this work in Electron Devices a couple years ago. So there's a picture of the diode. And we wanted to get a feel for its current voltage characteristics. The thing about gallium nitride diodes is if you're going to want to model its current voltage characteristics, you got to start with the band diagram, go back to all your physics that you took, your quantum mechanics, and you have to take into account all three current mechanisms. Thermionic emission, of course, when electrons are thermally excited over the barrier. Diffusion current, we all know what diffusion current is. Field emission, that's tunneling when electrons actually go through the barrier, so exploiting or leveraging the wave-like property of electrons. If you take into account all three of these effects, then you can write an accurate model for a gallium nitride diode because of the high doping. In the old Bethe theorem days with silicon, you didn't necessarily have to take into account all three of these effects. You could take into account the dominant one and still get an accurate model. So when you take into account all three current characteristics, that is, again, thermionic, diffusion, and tunneling, if I can switch, we get a model like this. Now, what I want to point your attention to here is I keep hitting the wrong button, I apologize. The black solid line and the black dotted line. The black solid line is the experimental data. We took that at HRL. The black dotted line is the model with all three effects taken into account. That is the thermionic emission, the diffusion current, and the field emission. You can see in GaN-based modeling, you have to take all three into account to get a good model. And the model fits at both 24 degrees and 80 degrees Celsius. So what can you do with that model? Well, you can write a SPICE. You can write a SPICE model with it. You can enter all those parameters into SPICE. It would be probably very accurate. It would be slow because there's a lot of parameters in that model. And it can be used to predict the circuit level performance. It would be amenable to what we like to call scaling rules in the modeling community. Scaling rules are, of course, how do you predict the performance of future higher voltage devices based on an architecture like this. This was a 600 volt device. Well, what does a 1 kV volt device look like? What does a 1.5 kV volt device look like, et cetera, et cetera. This type of model is amenable to that type of analysis. And then, of course, another advantage of this is that observed and simulated circuit performance can be correlated with underlying physics. The model is based on real physics parameters, so you can correlate what you're seeing in the simulation with actual physics parameters. But again, a very, very slow model, difficult to derive. You've got to be good at math, you've got to be good at physics, etc. What about circuit simulation? We've done work with SPICE, we've done work with Sabre, etc. So a couple years ago, we set out to import models of EPC GaN devices into Sabre. Now, Sabre uses like this automated optimization tool where you feed it certain curves, certain parameters, and it basically builds your model for you. So it's a lot of it's a behavioral model. It's not based on any physics. And you can see that, okay, these IV curves are pretty good, but they're, look at the CV curve here. CV curve is obviously very important if you want to look at the switching performance of the device. So the CV curve here is just it's just okay, right? My colleague Andy Lamont, he built a double pulse test stand at the University of Alabama. We took those EPC GaN devices, we put them in a double pulse test. We wanted to just look at the ability of Sabre or SPICE, whichever one we were using here, to accurately predict the circuit level performance of the model. So here's the DPT test stand. Again, this is at the University of Alabama. This is the actual circuit with some of the parasitics of the circuit characterized. Very important in wide bandgap semiconductor device modeling. If you want to get good waveforms, you got to know what the parasitics are. What's the bus inductance? What's the gate inductance? You have to characterize that, otherwise you're not going to get good waveforms like I'm going to show you on the next slide. So we actually ended up building two models of the device. One was from one modeling platform, one was from another modeling platform. We wanted to get a feel for which one was better, and I'll explain why in just a few seconds. But you can see that when you're doing time domain modeling, you're really looking for a couple things. You're looking for this ringing frequency. That tells you that you've accurately modeled the parasitics of the test stand, the inductance of the bus, the inductance of the gate, etc. You're looking for this slew rate here, this slew rate here, this slew rate there. That tells you that you've got a good model. You've got the IV characteristics right, you've got the CV characteristics within reason, etc. Now, you can see here that the ringing frequency starts to deviate from the actual experiment. And we think that's happening for a couple of reasons. We think that there's frequency dispersion going on. That is, the capacitances of the device are changing with the frequency, and our model doesn't account for that. So that's a limitation of our behavioral model here. Now, I mentioned before that we did two models. Here's a real cool thing about behavioral modeling is, number one, we started with this first model, and we measured its error. Now, we used like an RMS error function to measure the difference between the simulation and the experiment. And then we used a different model from a different vendor. Same device, two different models of the same device. That's one of the great things about behavior modeling. You can do this very fast. Now, here's what's kind of cool is from the original data set, from the original starting point, Model 1 had a higher error than Model 2. But after we ran some optimization using this mathematical curve fitting algorithms with some tuning, etc., the performance of Model 1 was significantly increased, whereas Model 2 could only be increased just a little bit more than by half, whereas this is 30 times and this is 2 times. And so with behavioral modeling, you have the time to do that. It doesn't take a lot of time to do that. With physics-based modeling, such a performance improvement would take us a long, long time. And so that's one advantage offered by behavioral models is you can fine-tune, you can improve your model in a faster, more efficient way. And that's what we're showing here with this improvement from Model 1 to Model 2. We published this work here in this paper. I encourage you to take a look at it. There's more specifics than what I'm giving you here because this is being recorded. But I invite you to take a look at this paper to try and understand how we were able to improve the performance of Model 1 as opposed to Model 2. So, behavior models. Circuit simulation standard models based on curve fitting. They can be tuned efficiently to achieve more accurate results. In general, behavioral models are faster. There's a little bit of a cost to accuracy as opposed to physics-based models. They're not amenable to correlating observed circuit performance to underlying physics-based parameters. Like I said before, with the physics-based parameters, you can see, observe a phenomenon at the circuit level. You can correlate that by simple, guess and test, not guess and test, but change something, observe, change something, observe. You can correlate behavior with physics-based parameters with physics models. You can't do that with behavior models. So that's one disadvantage of behavioral models. So that was kind of like a quick overview of the differences between physics-based and behavioral models. Now I want to do a little bit of a deeper dive on some of the things that we've done. And I'll start with a project that we have going on with the Navy. It's on simple edge termination design for vertical GaN diodes. What we were asked to do here was basically have a process flow, from device physics simulations, integrate physics with circuits to try and meet some kind of spec at the system level. Efficiency, power density, temperature, what have you. And if you're not meeting that spec, have a parallel optimization loop to be able to go in and tweak the device physics parameters that you need to be able to tweak to get that performance spec that you need at the system level. This is something that's really important to the folks who fund this. They want to be able to integrate this path in a very fast, accurate, and efficient way. So again, it goes back to the hierarchical energy infrastructure, semiconductors to circuits to systems. So what are the various physics-based parameters, such as JTE, junction termination extension thickness, intrinsic GaN depth, doping? How do you find the optimal value so that you can get a good yield in your fabrication to be able to design the diode, to design the device, to meet the application spec? That's what we set out to do. We were funded to do this, and we were funded to do this with the U.S. Naval Research Laboratory, in addition to Sandia as well. Sandia is working on this as well. So basically, they've got two thrusts that they're working on, or we're working on. This has changed a little bit in real time. So this was like the original objective, but things have changed a little bit. But basically, they had two thrusts. They had the manufacturability and reliability thrust. They had the high voltage proof of concept thrust. This one, of course, they're thinking a lot about cost. This one here, they want to be able to throw the kitchen sink at and just see if they can get to 20 kV. They wanted our help with the TCAD modeling. So this is what we started with. This is the original device they gave us. I have the specs of the device. I don't have them off the top of my head, but they're in this paper here. We just published this in Electron Devices. This is the original device that they gave us. I call your attention to just a simple isolation implant here on the side. There's a P++ capping layer underneath the anode that extends underneath the silicon nitride passivation layers. That P+ capping layer is hopefully to form a smaller contact resistance, but we find that it plays another role, and I'll show you that in a minute. So they gave us this structure, and they asked us to model it in TCAD, finite element modeling. So when you set out to make a TCAD model, finite element models, there's a lot of things that you have to consider. You want to consider GaN's low intrinsic concentration. You need to consider models for optical generation carriers. You need to consider the mobility variability, experiment and literature. There's a lot of differences between what you see in experiment and literature on those two topics. Defects and trap states, the contact resistance, and then of course the range of reported impact ionization coefficients. When we measure breakdown, we're basically wanting to see that ionization interval go to 1. We don't actually measure breakdown. We just look at the ionization interval until it goes to 1. So this is our simulated device structure of that same device that you saw on the previous slide. This is the mesh structure of that device. And of course, when you do finite element modeling, you have to have a good meshing. There are something like 100 to 150,000 elements in this structure right here. So when you take all that into account, obviously when you make a model, you want to compare the forward and reverse. This is diodes, by the way. So these are the forward curves here. We got our colors. Our colors here are confusing, so I apologize for that. On the left, measured is blue and simulated is right, but then it's the opposite on the right. So that's confusing. I apologize for that. But anyway, look at the forward curves. A couple things you're looking for to know that you have a good model of the forward curves. Number one is you want to look at the turn-on voltage. You can see we're getting the turn-on voltage pretty closely there. Number two, you want to look at the on resistance under high injection. That's the slope. The slope is pretty close, so it shows you a good model there. The third thing you want to look at, which is really important, is in the low injection region. So this is a logs. This is a look at a lower injection region here. So all the way down here, and you can see there's a little bit of a hump there. That's Shockley-Reed-Hall combination coming into effect for gallium nitride. You don't see those types of effects in conventional diodes, but you can see that in GaN. So you've got a good model here. Then what we did was we looked at breakdown voltage. I mean, the whole idea of this project was to optimize, implement, improve the breakdown performances of these diodes and use TCAD to inform that. So there's these different wafers, W1, W2, W3, W4. They all have different doping. And you can see that, hang on a second. You can see that initially simulating experiment break lesson, we didn't get quite the breakdown that we wanted from these models. We were expecting something a lot higher, particularly from W2 and W3 because they had lower P-GaN doping. I thought that was on the slide, but it's not. It's in this paper. I invite you to read this paper. It's a paper from Toledo. NRL and Sandia that we wrote on improving breakdown performance. But these two wafers here, they had lower p-GaN doping, and we expected them to have higher breakdown performance, but they didn't. So that's what TCAD allows you to do. It allows you to do electric field distribution studies to understand why the device is breaking down prematurely. So if we took a look at wafer 3 here, look at the electric field distribution, you can see that there's a lot of buildup here right against that P++ capping layer that I showed you earlier, which is extending underneath the anode and then underneath the silicon nitride passivation layers. So the electric field is not able to uniformly distribute across that P+ capping layer. So what we did was we went into simulation and we removed that P+ capping layer everywhere except underneath the anode. So we kept it underneath the anode so we can maintain that contact resistance, but we removed it from underneath the silicon nitride passivation layers. And then what you see here is you get much more uniform electric field distribution. You get an improved breakdown performance from 750 volts to 1800 volts.
Does the TCAD need a lot of calibration, or is it?
Well, that calibration I showed you before when we matched the forward and the reverse curve. But yes, it takes a long time to calibrate the model, a long time. Now, Naval Research Lab, this is Naval Research Lab's capabilities. How do you remove that and experiment? Well, they've got two things they can do. They can just etch that P++ capping layer, which they did here, or they can do a low energy implant to just blast it away. They've done the left, they're working on the right, and we talk about that in this paper. So basically they went ahead after we informed them that you need to get rid of some of that P+ capping layer to improve the breakdown performance. They went ahead and they did that. And here's what we get. So what am I showing you here? These are the experiments. This is all experiment here. So before they etched away that P+ capping layer, their device is breaking down at about 900 volts here. After they etched it away, they were breaking down at 1300 volts. So we're getting about a 50% improvement in the diode performance. And the leakage changed, yeah, exactly, yeah. So, in summary, what you have there is you have good agreement with the forward characteristics with TCAD, you have good agreement with the reverse characteristics with TCAD. After removal of the P+ cap, the breakdown voltage of the simulation was 1800 volts. The empirical breakdown was about 1300 volts. There might be some etching defects when they're etching that away, so we need to work on actually capturing all those effects when they etch it. That's why there's a difference between 1300 and 1800. But the trend is validated that, hey, you need to get rid of that P++ capping layer to improve the breakdown voltage. And so now that you have a partially or almost completely validated TCAD model, now you have the ability to make more improvements, to do more fine-tuning to that model to see, hey, how much more breakdown can you get at? What is the capability of this model? How sensitive is it to changes in doping concentrations, to changing in intrinsic GaN gap, etc. So we used our validated model to study these types of things. So, for example, we studied what is the breakdown voltage versus the p-GaN doping concentration. They were using magnesium there. Again, this is all in this paper. And we varied the drift doping. And so I call your attention to this blue curve here. The blue curve is at 1 × 10 to the 15th drift doping. And the parallel plane breakdown, that's what the simulation predicts is the most you can get out of that structure is 2200 volts. So what we're saying here is that for significant changes in p-GaN doping, 100% change from 2 × 10 to the 17th to 4 × 10 to the 17th, you're getting roughly the same amount of breakdown voltage out of this material, out of this device. That is a really, really powerful result. Basically, we're saying that this structure is very resilient to changes in process variation. Sorry, I keep skipping slides ahead. Very resilient to process variation, which is very powerful for wide bandgap semiconductors, particularly GaN, which we've known in the past is a little bit sensitive. Now, as we're varying all these things, we got to go back and make sure that there was no cost to the on resistance. And we did that study, and you can see it did change a little bit, but the slope is about the same in every single one of those curves. So what we're saying is even if you do this variation, even if you mess up a little bit in your experiment, you're not going to have so much cost to your on resistance. This device is very tolerant, and it's very scalable, tolerant to changes in process variation. What about the edge termination width? That's important for the die size. The die size, which impacts the cost of the device. So I call your attention to this purple curve here. This purple curve is again at an mg concentration of 3 times 10 to the 17th. What we're saying is for an edge termination width of 20 microns all the way out to 100 microns, you're getting almost the same breakdown voltage and very, very close to the parallel plane breakdown. So again, it's very tolerant to process variation. It's a simple edge termination design. All you did was you just got rid of that P++ capping layer, and you got yourself a 2,000 volt diode, which is very resilient to process variation. And all of that was possible because we did this modeling in TCAD. Now, what about the good old Polyga figure of merit? Again, we plot on-state resistance versus breakdown voltage. This green here is the theoretical limit of GaN, the well-known theoretical limit of GaN. These blue dots here are our simulated device. Okay, again, the better the device is lower and to the right. Now, the contact resistance that we're using both in simulation and at NRL, they're not the best. So what do we do when we go ahead and we take the best reported contact resistance from the literature, we swap out the ones that we have in our simulation, then we get the orange data points. So we're really showing that we're basically landing on the theoretical limit of GaN with this type of structure, once we use the best contact resistance. We use the ones that we have right now with these blue dots, just basically swap those out in simulation with the best reported ones. Now you're pushing the theoretical limit. So that is 2,000 volts, right? That's great, but we want to get this up to 20 kV eventually. So 2,000 volts is a good start, but we've got more work to do. So that design was okay, but now we have to start to think about more complex designs to really scale this up a bit. So we started to look at hybrid edge termination. Hybrid edge termination is basically reproducing Polyga's bevel here with a combination of guard rings and junction termination extensions. This bevel angle is really, really difficult to fabricate. It's hard to do. But can you basically reproduce this bevel angle with an optimized charge profile that consists of junction termination extensions and guard rings? Basically, we want to reproduce this charge using this structure. This structure, although it may not look like it, is much, much more amenable to fabrication than this structure. And basically, we wrote this paper recently in Transactions of Electron Devices. It's a different paper than the one I previously mentioned. We came up with this optimization procedure, which I'm showing you here. And the goal is to reproduce the amount of charge contained at any given angle. So we did a lot of math. I'll save you the trouble of that math. But basically, if you plot charge on the y-axis, on distance on the x-axis, you can compare what the bevel charge profile is. Again, that was work that was done by folks 20, 30 years ago. And this new hybrid edge termination that we're doing, you can see that we're getting spot on accuracy with the charge profile with our optimized structure. Again, replacing the bevel with a combination of guard rings and junction termination extensions. And this is the math that we do to be able to do that. Again, I invite you to read this paper to get a closer look at that math. We need to figure out what the optimal amount of guard rings is, because that can change the breakdown voltage. So what we found is that with 4 guard rings and with 12 guard rings, we're getting the highest amount of breakdown. The blue line here is the reference bevel. That's, again, work done 20, 30 years ago. Then the red circles here are our optimized hybrid edge termination. And you can see that we can get pretty close to their breakdown voltage. And then the parallel plane breakdown is just above that. So everything's all in the same neighborhood. This this amount of disparity, I would call that not very significant. But look at the isolation implant only. That's the previous structure I was showing you before, that simple edge termination. That can't get anywhere near to this type of breakdown. So we built the older one, the bevel one, from 20, 30 years ago. We built that in TCAD. We studied its electric field distribution. You can see this one is breaking down at 2,550 volts. Then we built the 4-ring structure. Remember that previous plot I showed you. 4 and 12 had the best performance. And how do you compare them? How do you compare this with this? They kind of look alike, maybe, maybe not. What we do is we do a cut line. At any given point, we do a bunch of cut lines to study how the E field changes at any given point along the PN junction. And I'll show you that momentarily. What about this is the 4-ring structure. What about the 12-ring structure? Now, the 4-ring structure is breaking down at 2,500 volts. Let me go back a second here. The reference one's 2,550. The 4-ring optimized structure, 2,500 volts. And the 12-ring, 2,400 volts about. Again, now the question is, how do you compare are their E fields the same? Are they not the same? This is very subjective, right? This is very subjective. But what we can do is we can plot cut lines along the PN junction. And that's what we did here. So on the left-hand side is a comparison. Sorry, I really struggle with this thing. On the left-hand side is a comparison of the 4-ring structure with the reference bevel. Again, this is the electric field along one cut line. And then on the right-hand side is a comparison of the 12-ring structure with the reference bevel. So what you can see is our E field at times is above the reference bevel, at times it's below the reference bevel. On average, it's about reproducing it, right? Again, here, our E field above at times, below at times, but on average, it's reproducing it. And again, why is this important? The hybrid edge termination structure is more amenable to fabrication. It's easier to fabricate than the reference bevel. So we do some process tolerance. Again, just like we did before, just to see how tolerant this structure is. And so again, we measure the breakdown voltage versus the P-GaN doping. There's a lot of data here. Basically, the most important thing you want to look at is the red curve, which is the reference bevel, the work done many, many years ago, and then the, oh goodness, this, what would you call that? Cyan, purple, magenta. I forget color names. Magenta. You can see that it's pretty tolerant to the changes in the P-GaN doping. And NRL we're publishing another paper that's verifying these process tolerances. What about the P-GaN thickness? Breakdown voltage versus P-GaN thickness. Again, the important one here is the reference bevel, and then you're looking with the magenta as well as the green. So the green is not the 4-ring structure. Oh, here's the trade-off. The 12-ring was a little bit less breakdown, you might recall. It was 2440, whereas the 4-ring was 2500. But the 12-ring, as I'm showing you here, has more process tolerance than the 4-ring. So that's the trade-off. Do you want more magnitude and breakdown, or do you want more process tolerance? I think for the change in breakdown between the 4-ring and the 12-ring, you'll take that process tolerance with the 12-ring. So those are the things that you want to think about. Now, we're using this optimized strategy right now to go ahead and build 3 kV, 5 kV, 7 kV diodes. Hopefully, some not too long day down the line, we'll use this type of structure to really start to push voltage well above 10 kV. And you should look out for some more papers from us on that. But this procedure, this optimization procedure is now proved. It's in the literature, and we are in the process of using it to really push the theoretical capability of GaN diodes to really get well above 10 kV in a simple, manufacturable, cost-effective way. Okay. Let's talk about silicon carbide for a second. Now, I want to reiterate something. I did GaN physics-based models, and now I'm going to do silicon carbide behavior models. That doesn't mean that we can't do silicon carbide physics and we can't do GaN behavioral. I just picked some projects here that I wanted to show you. So, you know, there's no preference for one or the other. We wanted to study something interesting with silicon carbide, and I alluded to it earlier. We think that as these frequencies are getting higher, as the switching capability of these devices are getting faster and faster, we're now injecting the type of harmonic content that we had not seen in the power electronics community before ever. It's going into that near RF regime that I talked about before, that Professor Amy Lamani likes to talk about. And there's some work done by a professor at Chalmers University, Professor Angelov. I don't know him, but he's kind of reported on something similar. So I hate to make this sound like an elementary story time, but I'm going to read this to you. One of his papers, he writes, when the time domain waveforms are measured at high frequencies, the contribution of the channel current is mixed with one arising from the transistor's nonlinear capacitance and is therefore not distinguishable. DC measurements can be used as a starting point for the modeling of channel current. Nevertheless, for transistors fabricated with compound semiconductors, the channel current measured under static conditions may differ from one measured under dynamic conditions due to dispersive phenomena such as charge trapping mechanism. What did all that mean? Let me just translate all that. Basically, what he's saying is that using DC measurements alone is not enough to predict the time domain behavior of a wide bandgap semiconductor based on compound semiconductors. You need to characterize how the device changes at various frequencies, and only then can you build a good simulation model. So, and he's talking about dispersive phenomena. He's talking particularly about how perhaps the internal electrode capacitances, CGD, CGS, CDS, how they change with all the injected harmonic content in the circuit.
And with time, which is charge trapping.
Yeah, exactly, exactly. So this is kind of like our hypothesis. This is not real data I'm about to show you. This is our hypothesis of what we think happens with dispersive phenomena. So as the frequency content within the circuit starts to change, you know, you have constant capacitance, although it's changing with voltage, then you go back past a certain frequency, we believe you'll see a drop in the capacitance. We believe you'll see a drop in the capacitance. That's our hypothesis. So let me just show you that again. We know that capacitance is voltage dependent, okay? Everybody knows that. But we're trying to prove that, hey, when you do a device model, you have to take into account this frequency dependence. And that frequency dependence comes into play past a certain frequency. That's why you never had to worry about this in silicon-based power electronics, because we never pushed those frequencies. But with wide bandgap semiconductors, we think that we're pushing those frequencies. So we think that the capacitances will eventually become frequency dependent. So we set out to try and model this. Okay? How do you model the frequency dependence of these capacitances? This is what we did. We imported MATLAB and SPICE, and we built basically a two-level model. The first level model is just a static model. By static, what do I mean is we match the IV curves and we match the CV curves, just like you would in any conventional behavioral model. All right. Then we instantiate that model and we compare its circuit performance with the experiment. But then we also implement a dynamic model. In the dynamic model, we keep the IV curves constant. We don't touch those. And we allow the C's to change. We allow also the parasitic inductances to change within the bounds of their uncertainty. We think that the parasitic inductances will also have some frequency dependence to them as well. So we allow the inner electrode capacitances to change with frequency, and we allow the parasitic inductances to change within the bounds of their uncertainty. That's what we call dynamic tuning. So there's static tuning up here, and then dynamic tuning. We then compare the performance of the static model with the dynamic model. This is a little bit controversial. I mean, a lot of folks will tell you that this is the traditional way of doing this. You can't go beyond this. What we're trying to tell you is that if you're going to talk about the types of frequencies that we're talking about with wide bandgap semiconductors, you have to include this dynamic modeling. Otherwise, you're never going to get to an accurate model. So hopefully I can make the case for that here today. So we simply use, as an optimization algorithm, with behavior modeling, you need some sort of optimization algorithm. we use the well-known downhill simplex algorithm. It's the Nieder-Melder, I think it was, algorithm. It's a very well-known algorithm made back in the 1960s. It does 4 things: expand, contract, shrink, etc., to go and find its optimal points. Derivative-free optimization algorithms, very, very important so that you don't have continuity issues with these types of models. So we basically picked any IV curve, any known IV model that we want, and we use this as the optimization algorithm to build a very accurate static model. Again, a very accurate static model. This was a 1.2 kV silicon carbide MOSFET, and I hope you'll agree that this is a very accurate static model. This was not our model. This is just a reported model that many people have used. We used the model, and we used the downhill simplex optimization algorithm to build the model, to get this type of accuracy. So when you're talking about a FET, you want to look at a couple different things. You want to look at the saturation region. That tells you that you're going to capture the switching correct. You want to look at the linear region. That tells you that you're going to get the conduction correct. With silicon carbide, there's always this gradual transition between the linear and saturation regions. You want to make sure you get that right. The arctan function is very good at doing that. And you can see we have a very accurate static model. We use the same model, again, and the same optimization algorithm to get the capacitance versus voltage, or in this case, charge versus voltage. Q is equal to C times V, as you know. So it's a very, very accurate model. This is, again, we published this in Transactions on Power Electronics a couple years ago. It's basically taking a known model and a known optimization algorithm and combining the two to make a very accurate static model. So then my colleague, Professor Lamont at the University of Alabama, he builds, again, his DPT. He characterizes his test stand, and he takes empirical measurements on the silicon carbide MOSFET. And we compare the behavior of the static model with the experiment. So what you're seeing here, the solid lines are the experiment, the dotted lines are the model. On the left is turn off, on the right is turn on. I hope you'd agree that the curves that I showed you on the previous slide, you couldn't make any better curves. We had almost a nearly perfect IV fit. We almost had a near perfect CV QV fit, CV, and yet we're not getting a very accurate time domain result. And we've seen this. Now, this is just one data point I'm showing you. But we've seen this in a myriad of other projects that we've taken, both with GaN and silicon carbide. It's simply not enough to just model the static IV and CV curves. You have to bring in some frequency dependence into it. So that's what we did. So to a first order, this is very, very simple, very, very basic. We're working on refining this, but we did publish this work in Transactions on Power Electronics a few years ago. What we did is we modeled the input capacitance as some constant K. K can only vary between 0 and 1 because remember, we think capacitance is going to go down as frequency gets high. CGS plus CRSS. CRSS is just CGD. We let COSS, again, some constant K, which only can take on values between 0 and 1, times CDS plus CGD. And then, of course, CRSS, some constant K, which only can take on values between 0 and 1, times CGD. And then we also allow the parasitic inductances, the gate, drain, and loop inductances, etc., to vary within the bounds of their uncertainty, accounting for a couple things. Number one, the frequency dependence. Number two, there's uncertainty in those measurements. And this part here is definitely accounting for the frequency dependence of the capacitance, we think. Now, this is our dynamic model. So I showed you a few slides ago our static model. This is our dynamic model. I'm sure you're dying to see a side-by-side comparison. Let me do that for you. So this is the dynamic model. This is the static model. Let's go back to the eye doctor. Remember the eye doctor? Better 1, better 2. Better 1, better 2. I hope you'll agree better 1. In this case, now, better 1 meaning the dynamic model after we did dynamic modeling. So again, when you're doing time domain modeling, you want to look at the slope here, the slew rate. That makes sure that tells you that you have a pretty accurate device model. You want to look at the ringing frequency. That tells you that you're modeling the capacitance accurately and you're modeling the inductance accurately. Yes, sir?
That frequency axis on the where you had the roll of capacitance, how do you define the frequency? Is it 1 over the turn-off time, or is it an actual driving frequency of the switch, or what?
So in this model, this is a pretty simple, good question. So this is a pretty simple model. We're just letting K vary between 0 and 1 until the model agrees. In the future, what we need to do is we need to measure C at various different frequencies and find the frequency at which it changes, and then write a feedback loop within MATLAB or SPICE to say, hey, as that slew rate is changing, go and extract the new value of C. And we're working on doing that right now.
Sorry, I guess I'm saying I haven't seen anybody switch silicon carbide at the megahertz and above. That's just me, so I'm still asking what the meaning of that frequency was.
Gotcha. Got your point. Got your point. Sorry, I misunderstood your question. It's not the switching frequency. It's the frequency of this ringing, which is orders of magnitude higher than the switching frequency. The capacitance will change at this frequency, not the switching frequency, or the frequency associated with this rise time, fall time. And that is tens of megahertz. I'm sure you'll agree. I agree with you that we're not switching silicon carbide at tens of megahertz, but the frequency content contained in the signal is well into the tens of megahertz. That's that near F stuff that I'm talking about.
Thanks.
Great question.
So can I ask you, so what you're trying to do here now is just to change those parameters K so they sort of match, and then figure out why they need to be a different value than one later.
Exactly.
That's the deal.
Yeah, exactly. And I'm going to show you that on the very next slide. That's what you just said, right? Professor Lamont at the University of Alabama, he measured his drain inductance, his gate inductance, his source inductance, and then from the dynamic tuning, we extracted these values here. Is that uncertainty? Is that frequency dependence? Is it both? We don't know yet. But what about the K values you just mentioned? So their ideal values, or their nominal values are 1, right? That's the static measurement. But then when we let them vary, as you said, here's what we're extracting: 0.97, 0.87, 0.9. Hopefully making the case that, yes, there is some frequency dependence that we need to look into here. So this is a very first order approach to doing this, but we're working on more refined ways of doing it in the future.
Excuse me?
Yes, sir.
So what kind of physics do you think is the frequency dependent of the capacitors?
You mean the capacitive dispersion?
Yeah. I mean, beside the charge trapping?
Charge trapping.
Only charge trapping.
Yeah,
right?
yeah. That's what I think.
Okay.
Now, this is not enough, right? This is not enough. I just showed you one data point and I tuned my model to it. I have to do something else very, very important. I have to change the operating condition and then take my tuned model and compare my tuned model with that experimental operating condition with no tuning. Then I've got more of a case to make. So let me just kind of repeat myself here. The previous operating condition was 600 volts and 10 amps. I tuned my model to this operating condition. I've got a good fit here. That tuning led to these extracted parameters here on the bottom row. Now I populate my model with those extracted parameters. I change the operating condition and I do another comparison at what we call an orthogonal data set. You can't validate your model with the same data point that you used to validate it, right? So we got to change the operating point. So we kept the voltage the same and we doubled the current from 10 amps. What did I have before? I forgot already. 10 amps. 10 amps, we went to 20 amps. And you can see still a pretty good fit there. Still a pretty good fit there. So this is gaining traction. There are other, not just us, but there are other people starting to say, hey, you really got to take a look at the frequency dependence of these capacitances to write a good, accurate, precise model. All right, I'm winding down here. I just want to talk about some very quickly. I want to talk about some applications in space. this is our testing. I highlighted a lot. My friend and colleague, Professor Lamont at the University of Alabama. I wanted to take a minute to show you our test stand at the University of Toledo. We've got a solar array simulator there. We've got all kinds of power electronic characterization equipment. We're doing some work in maximum power point tracking. I'm sure most of you know what that is for photovoltaics. This work is being sponsored by NASA. They're interested in how radiation affects their ability to track maximum power in space. So we're doing work in both radiation and in maximum power point tracking. We wrote an algorithm that takes into account partial shading conditions. I'm sure you know what those are. When there's lunar dust, say on your solar panel on the moon, there are these various local maxima and global maxima. You don't want your algorithm to get caught in these local maxima. You want it to be able to track these global maximum. So we basically wrote a sampling algorithm that allows you to track the global maximum.
You have to jump around a lot more.
Yeah, that's what I'm about to show you here. This is work we just published in Transactions on Industry Applications, where we wrote a two-level algorithm. In the first algorithm, we used that sampling out. In the first level of the algorithm, we used that sampling approach, which I just showed you in the previous slide. And then so that basically, what that does is it hones in on the neighborhood of the global maximum. So what the sampling does is you invoke that, it finds, okay, the neighborhood has to be somewhere here. It doesn't know where the max is, it just finds the neighborhood. Once it finds the neighborhood, we invoke this very well-known algorithm called ripple correlation control. That's not ours. That was reported by folks at University of Illinois Urbana-Champaign 10, 15 years ago. It's a very, very good algorithm, very, very accurate. So basically, RCC says, all right, now I know where the neighborhood is, now I'll go and find it. So we did a comparison of our algorithm. We did our algorithm, the two-level approach. Again, the sampling algorithm in the first level with RCC in the second level. We used our sampling algorithm in the first level and then the well-known perturb and observe algorithm in the second. And then also just RCC, just ripple correlation control, meaning no account for partial shading conditions. So the conditions changed. We went from a uniform irradiance, no partial shading, to a partial shading condition 1, partial shading condition 2, partial shading condition 3, and then a uniform irradiance condition 2. And you can see that the blue is the theoretical maximum power point. The red is experimentally extracted maximum power point from our power electronic characterization equipment, which I showed you. You can see we're always able to track it. Perturb and observe is not able to do it with quite the level of speed that the, RCC is with the sampling algorithm in both. Then if you just use RCC, RCC is wonderful. Don't think for a second I'm bashing it. It's a wonderful, amazing algorithm. But by itself, it cannot account for partial shading. So you need our sampling algorithm to be able to account for partial shading. So our friends at NASA are really interested in this type of work. And here's why. So as many of you, of course, know, you have a power conversion system. A cosmic ray in space can hit this power conversion system. It can cause all sorts of radiation-induced damage. This is an area where I'm sort of learning on the job. That's not my training, but I've been learning a lot. We just published a paper here in IEEE Transactions on Nuclear Science. Because the cool thing is you can use TCAD to do radiation studies as well. And so what we did is we worked with the Naval Research Lab to build a model of their 600-volt HENT device. So the same principles that I talked about many slides ago. IV forward curves, IV transfer curves. They're using something called two-photon absorption at NRL that kind of mimics heavy ion implantation, except it's not early heavy ions, it's two-photon absorption. You can do that a lot faster, it's a lot quicker, and perhaps less expensive than heavy ions. And it also, another really important thing about two-photon absorption is you can hone in on certain areas on the device and really try and figure out where the sensitivities are. Whereas with heavy ions, it just obliterates the whole thing. You don't know where the sensitivities were. So that's one real cool thing about TPA. So we built a model of their HEMT device, and you can actually, in TCAD, you can simulate ion strikes, which is really cool. And you can see how much charge is collected with those ion structures to really study the radiation tolerance of these devices. And so, oh, that's really blurry. Sorry about that. But this is some work where we basically took a look at the charge collection and the current as well. And this is all from both TCAD as well as an experiment, which I'll show you on the next slide. Again, we just published this in Transactions on Nuclear Science. And you can see that the simulation can be used on average to capture what the experiment is doing. Again, this experiment is 2-photon absorption, not heavy ions, but there's been previous work that shows that those two give similar results. So another cool thing you can do with TCAD, gallium nitride particularly has some great radiation tolerance, really good for pushing the limits in space. Let me wind down here. Behavioral models versus physics-based models. Behavioral models are generally faster. Physics models are generally more accurate. Behavior models are more amenable to model refinement because they're faster, they're quicker to improve, as I talked about earlier. Physics-based models are more amenable to correlating observed behavior with underlying physical device parameters. I almost tripped over my feet there. And scaling rules. Scaling rules. How do you take a validated model and then use it to tweak physical device parameters to project the performance of future higher voltage devices, 10 kV, 15, 20 kV? That's one great utility of physics-based models. And we're always looking to hybridize the two, the behavioral and physics-based models. Those of you who might have studied Cedra-Smith, that very well-known equations for MOSFETs, that it could be argued as a hybrid model between it has physics-based parameters and it also has mathematical-based parameters. So we should try and hybridize the two. As we move forward with wide bandgap semiconductors, we need to reduce the parasitic inductances so that the value proposition of wide bandgap semiconductors can be fully leveraged. Basically, a lot of times we find ourselves having to slow the device down, slow GaN down, slow silicon carbide down, because if we don't, then the parasitic inductances will disrupt their behavior, the thing blows up, and it's like, why? And then if you're slowing it down, it's basically no better than the silicon device. So, we're not able to fully extract its value proposition. So we really need to work on fine-tuning parasitic inductance. We need more sophisticated models to capture this frequency dispersion that I was telling you about. That model that I presented does a very simple way of doing it, which is basically letting K vary, right? We really need to do something that's a little bit more physically involved, accounting for those trapping effects, etc. Ultra-wide bandgap devices can potentially push 50 kV, and that was Edison's dream, HVDC distribution, right? 120 years ago. So we want to explore what we can do with ultra-wide bandgap devices. So we can't do that until we push GaN and silicon carbide to their theoretical limits. Radiation tolerance, I was just talking about, enable deeper space penetration, but also think about nuclear, some of these languishing nuclear power plants all across the country. Nuclear power is coming back with hydrogen. It's another area where I've done a lot of work. I didn't get a chance to talk about it tonight. Keyshawn wanted me to focus on semiconductors. But with the ability to generate low-cost carbon-free hydrogen, nuclear power is interesting again. And so that also opens up the opportunity to really explore the radiation tolerance of wide bandgap semiconductors. So you can put those power electronics right next to your reactor and save on a lot of the efficiency losses that way. So that's some other things that we really need to think about, not just for space, but for nuclear power. I leave you with this graphic. This is kind of like the tension between models, all the way down at the physics model, physics level, circuit simulation level, system level. We have all these random different platforms that we use. We all got to work together on this. If you go to the conference, edit this out, please. You go to the conference, people are saying my platform is better than yours, your platform is better than mine, yours has no physics, yours has too much physics. We got to work together. We're all trying to make these devices better. So this is the challenge we're up against, getting all these models to work together. So how do we do that? That's something that we all need to think about. I take a lot of the credit, but really it's the students who do the work. So there's a picture of my folks there. They're really great students. These are the folks who fund us and the folks who we work with, so I'm really, really grateful to them for all their help. Thank you all for hosting me today. To the Bay Area Pell Chapter, to the university, to our sponsors. There's my contact information, and I'm happy to take any questions that you might have. Thank you.
You indicated that you have this 12-segmented termination. You know, what is it? Is it just a photolithography that keeps you going up to 24 segments? So you got to make smaller and smaller gaps, and you're trying to use cheaper lithography tools?
Exactly. Yeah. It's easier that way. It's much easier than the bevel. The bevel is that angle that folks from years ago used to work on. It's very difficult to get that angle, and if you're off just a little bit, 0.1, 0.2 degrees, your breakdown voltage will change considerably. So what you're saying is exactly a more cost-effective way of doing it.
Would it help to go from 12 up to 20, or your model showed not very much help?
So what it would do is you would get more tolerance on process tolerance, right? But then you would also need to redo the optimization to make sure you get the right charge for the amount of breakdown that you want. So, but we've shown that optimization algorithm can work for any breakdown voltage that you need. So the answer is you'll get more process tolerance, but you'll lose a little bit on breakdown voltage. Thank you. Yes, sir.
I have a general question. A lot of times the problem with studies like this is that you don't know if you're really at a local or global optimization point. So whenever you say I collected data and you say I use 600 volts, why 600? Why use 10 amps, 20 amps? Why 20? Did you kind of do a design experiment kind of thing, look around 600, look around 10, and how many times did you measure it? How many devices did you measure?
Are you talking? So, which project are you talking about? The TCAD or the silicon carbide one?
The one that you collected data on.
We collected data.
Silicon carbide.
Yeah.
The facts.
Yeah.
So you're talking about the silicon carbide one?
So you said I did 600 versus at 10 amps, and then I tuned it. Then I tried at 20 amps. Why 600? Why 10? Why 20? Why not 15? Why not whatever? How did you?
So the voltage is pretty easy to. So the basic operating condition for these things is half voltage, full current, and so that was a 1.2 kV device. So we ran it at 600 volts, and the full current rating, as we know, is what's the most current it can run without the thing heating up too much. And so I think 10 to 20 amps is in that area. But your point is well taken that you can't just show one data point to make these types of generalizations. But we have certainly done, and other papers have shown this as well. We've done this at other operating points. We have absolutely done this at other operating points.
A lot of times someone will tell you this is the spec, this is my device, run it here, run it there. But they played with it to find a place that looks good.
Of course.
So if you go there and do it, what does that mean? You have to kind of see how big this window is. And
no, I agree with you. One data point's not enough. I totally agree with you. But we have seen this at multiple operating points.
For sure. Measured it multiple times on multiple devices?
Multiple times, multiple operating points.
No hysteresis.
And there's not just one paper on this, there's other papers on this as well. Yes?
Okay. I would like to ask, have you tried your dynamic model on the gallium nitride and predict the Fmax and the FT? Can you predict the Fmax and the FT?
Fmax and FT, cutoff frequency, and what do you mean by Fmax?
Fmax.
Maximum switching frequency or maximum operating frequency?
Yeah, so that one consider the parasitic also, the Fmax.
Power transfer. Right?
Yeah, power, unity.
Yeah, I know the cutoff frequency is where the gain goes to 1, right?
Yeah, the other is power gain.
Yeah. We have not used it to do that, but I don't see why you couldn't.
Okay. But haven't tried it yet.
We have used it with GaN though. We absolutely have used it with GaN. If you take a look at that, in the first couple slides I showed you some work from APEC. We use dynamic modeling for GaN as well. So that goes back to your point that we've done it with GaN and silicon carbide. But we have not used it to predict the cutoff frequency. I'm sure you could, but we haven't done that yet.
Okay.
Yes, sir.
Yeah. When you're using the K factor and that sort of approach to optimize for looking at that ringing, won't that, however, screw up the modeling of large signal charge transfer that you'd be looking at for instance, for efficiency? Since clearly what you have is you've got a case where you're interested in the ringing frequency, and that requires one particular capacitance. But you're assuming because of dispersion, the capacitance is different than it is in the static case, right? So if you use that model, your static, there's sort of results that depend on static capacitance.
So okay, so great point. So that's a great point. So let me see if I can address that. Here we go. So the static one is certainly going to fit this initial slew rate, right? But the extracted value is an aggregate of fitting both the slew rate and the frequency. So it's an aggregate. It's not just one that's fitting just one thing. It's fitting the whole thing. You understand what I'm saying?
Yeah. I see. When you curve fit this, because of the nature of the test case that you're curve fitting, you should see both.
Exactly.
So you'll end up with a compromise.
Yeah.
But the best compromise. Okay.
Right,
Which is
right.
Yeah.
And we used. I should mention that we used a different type of error in this type of calculation. So there's like least squares, RMS type errors, but those can sometimes be misleading because you can have, think about this, say something goes up to 5 volts and rings at the right frequency, and say you have something that goes up to 10 volts and rings at the right frequency. If you subtract the two, you're going to get a 5 volt difference, but the shape is right. Now, what if you had just a step function that goes up to 10 volts? Actually, if you subtract the 10 volt ringing one minus the 10 volt step one, that error would be less than the 5 volt ringing one. So how do you come up with a good error? Well, what we did was we did something that looks at overshoot, percentage overshoot, attenuation coefficient, as well as frequency ringing to take in, that's what we call template matching. And we talk about that in this publication. That really gets you a compromise for all the different features of a waveform. Yes, sir.
So those coefficients that you determined are for a given ringing frequency, right? But ideally, those factors are also functions of frequency, right? As frequency changes, so K's do.
Yes. Okay. I want to make sure I understood the question. So basically, we're allowing K to change so that we can minimize the error between the experiment and the simulation.
Right. But the K that you've shown in that table is for this given ringing frequency, right?
Correct.
If the ringing frequency was different, then the K
would change. Yeah.
Okay.
Yeah.
So are you trying to figure out?
So that goes back to his question, right? So how do you change the ringing frequency? Well, you can do a couple different things. You can change the device and have a different capacitance, or you can change your test band and have different parasitic inductance. And yes, we're absolutely looking at that for sure. So K, so this is a great point. So it's not necessarily that you're tuning just the device model. You're kind of tuning a packaged test band, and then you're allowing yourself to move that test band, a validated model of that test band, into a larger simulation like a MVDC grid of a ship or of a terrestrial microgrid, and then really get a feel for how this thing would operate in such an application.
Okay. Thank you.
Yes, sir.
TCAT would be used for your simulation? TCAT tool?
Yeah.
Which one did you use?
I was avoiding saying that. It was Centaurus.
Okay.
Which one?
Centaurus, by Synopsys. Yes.
You said you were working with Sandia Labs. Did you use their Zeiss simulator for behavioral modeling?
We didn't use any of their simulators. No, they are involved with this development of vertical GaN diodes. They send their epi layers over to NRL, and NRL fabricates it, edits this out, please. and then we use that whole process.
So whose simulator do you use for behavioral modeling? You had to list a bunch of things listed.
Saber.
So the behavior model that we did before was so the silicon carbide was an integration with MATLAB and SPICE. Earlier in the beginning, I showed some other behavior models. That was Saber for GaN hence.
I don't think I've heard of anybody using Saber in years. So,
Oh, really? In industry, it's used quite often. Academia, I don't know. But there's a lot of folks in vehicle electronics use a lot of Saber.
yeah, it's kind of in its own market. I'm working with teammates stuff at the moment, and they said to use Simplest.
Or Simplorer by ANSYS. So Saber and Simplorer compete a lot. Have you heard of Simplorer? So that's an ANSYS program.
Yeah. Well, I've been to ANSYS talks, but I don't think you've ever mentioned that one. So.
Simplorer. What are they? Q3D, Maxwell, those types of things. And then they also use Simplorer for circuit simulation.
Do you see a need for thermal modeling?
Oh yes, there's an absolute need for thermal modeling. You want to with GaN. There's self-heating effects, and TCAD can do that. As my friend here would probably tell you, TCAD you can include self-heating effects. So in that list of provisions one has to consider when making a TCAD model, I should have put self-heating effects in there. Thank you for helping me. Yeah, that wasn't on that list, but it should have been.
Have you looked at using AI techniques for generating models where you're less restricted to what models we use?
That's a buzzword these days. If you look at every NSF-funded program in device modeling these days.
I was thinking more like Bernard Woodrow stuff, which goes back to the 70s.
Whose stuff?
Bernard Woodrow.
Oh.
We had them do a talk at CS a few years back.
I haven't used any AI, but I'm seeing a lot of that come out, and I'd like to learn more about it. I'm not trained in AI, but it's definitely something I would like to look at.
So it's languages like parallel ENS or parallel gauge are probably quite good for describing neural networks and like kind of doing that modeling automatically.
Yeah, I mean, if you see, I see. This is again, a little bit controversial, but I see a lot of NSF proposals being funded which have AI for semiconductor device modeling, and that's not something I've ever done. I'm sure it's great, but I've never done it. So, would love to chat more about that.
Let's give a
Okay, thanks, folks.
Thank you.